This video is about acids and bases and the net ionic equations that come when they react. Alright, first let's define our terms. There's actually several ways to define acids and bases. The one we're going to pick is the Bronsted-Lowry definition. Bronsted-Lowry definition. It's a middle-of-the-road definition. It's not the easiest, it's not the hardest, but it's the one most people go by. So this is the one we're going to pick for now. An acid, according to the Bronsted-Lowry definition, it's a proton donor. And by proton, what they mean is H+. An acid is something that's going to give off H+ ions in solution, which makes sense. If you think about all the acids that we named back when we were naming acids, they all began with H. So H+ donor is what an acid is. By the way, pH stands for negative log of the hydrogen ion concentration. So when you're talking about pH, you're talking about a way to measure how much H+ is in solution. Remember that the lower the pH, the stronger the acid. So low numbers, low pH is acidity. The lower the pH, the more H+ is. pH, by the way, you'll notice is a log scale. That means we're talking about a factor of 10 concentration of H+ when we're talking about changing one digit of pH. So if pH is equal to 1, that means the H+ concentration is actually 0.1 molar. Remember that capital M stands for moles per liter. If the pH is 2, that means the H+ concentration is 0.01 molar, 10 to the negative 2. So take a look at what pH means. It means every time I go up 1 pH, I'm diluting the solution by a factor of 10. There is a factor of 10 less H+ concentration. By the way, you're wrong if you think pH scale only goes from 1 to 14. It actually can go in the other direction, lower than 1, higher than 14. But 1 to 14 is the normal pH scale. Anyway, let's define base. Base. If an acid is something that donates H+'s, a base is something that receives or accepts those H+'s. Okay? So an acid is something that donates the H+'s and the base picks it up. That's the Bronsted-Lowry definition of acid and base. Okay, now what are examples of acids and bases? Common acids, acids that you think of, vinegar is an acid, acetic acid. Citric acid, the stuff in your lemons and your limes and your oranges. The common base would be ammonia that you clean with. A common base would be drain cleaner. All those things are bases. Now, the thing about acids and bases is we can separate them into strong and weak. Both acids and bases come in two varieties: strong acids and bases, weak acids and bases. In your book, Table 4.2, page 125, you will see they tell you common strong acids and bases. Common strong acids: hydrochloric, hydrobromic, hydroiodic. Not hydrofluoric, you'll know. HF is not on this list. HCl, HBr, HI. Chloric acid, HClO3. Perchloric acid, HClO4. Nitric acid, HNO3. sulfuric acid, H2SO4. Those 7 things are the strong acids. You probably should memorize those. Those are the strong acids. Now what about bases? Bases, or rather strong bases, are group 1 metal hydroxides. That is lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. So group 1 metals, alkali metals, attached to OH minus. Strong bases. Group 2, alkaline earth metals. Those guys attached to OH. Those are strong bases. Any other acid you see that isn't one of these 7? Weak. Any base you see that is not one of these guys. Group 1 metal bonded to OH minus, a group 2 metal bonded to OH minus. Weak. Now why is this important? Because strong things dissociate completely in water. Weak things do not. They only dissociate a very, very little bit. Okay? And this is important when you're writing your net ionic equation. So, let's start simple. A strong acid plus a strong base. Okay? One of our strong acids, most common strong acid is HCl. The most common strong base is NaOH. There's my acid. These are, of course, aqueous. They're dissolved in water. So my strong acids reacting with my strong base. Oh, look! It's a double replacement. I'm going to get H bonded to OH, which is what? It's water, obviously. Liquid. Plus Na bonding to Cl. NaCl, aqueous. Salt. NaCl is salt. Now, by the way, NaCl is table salt. But it is only one example of a class of compounds chemists call salt. Any acid plus any base always gives you water, and whatever else it gives you is called a salt. An ionic compound. Something plus, something minus. Add compound. That's called a salt. Okay? So salt is not just the stuff on your table. It's a whole class of ionic compounds that come when you mix an acid and a base together. An acid plus a base always gives you water and a salt. Now, let's think about this in terms of a net ionic equation. HCl is a strong acid. Now, what did I just say about acids? Strong acids dissociate completely in water. So if I'm writing my net ionic equation, or let's write the complete ionic first. Instead of HCl in water, I really have H plus ions, aqueous, plus Cl minus ions, aqueous, because they're dissolved in water. NaOH, strong. Once again, strong things completely dissociate in water. So I really have here not NaOH, but Na pluses and OH minuses. Those are my reactants, all of my ions. Now over on the product side, water is not an ionic compound. Water does not dissociate. It's covalent. Covalent things do not dissociate in water. So, water, still water. H2O. Liquid. Plus, but NaCl, That does dissociate in water. Na plus aqueous plus Cl minus aqueous. Oh, look! Spectator ions. Na plus sitting there at the beginning, floating about happily. Nothing happens to it. Still there at the end. Cross it out. Cl minus. There it is. Beginning, end. Hasn't changed. Bye. Now remember, they're still there. We're just ignoring them. That means my net ionic is H plus OH minus yields H2O. This one's liquid, that one's aqueous, and that one's aqueous. See this equation? H plus OH minus yields H2O. That is always your net ionic if you have a strong acid plus a strong base. Okay? Strong acid plus strong base always gives you this as your net ionic equation. H plus OH minus goes to H2O. It doesn't matter what the other ions are. It doesn't matter what the anion of the H plus is, what the cation of the OH minus is. Those are always spectator ions, and spectator ions never show up in the net ionic equation. What if, however, one of them is not strong? And it's never, by the way, that both of them are weak. Always one's strong and one's weak. It isn't only that we rig it that way, it's actually true no matter what, because always one is going to be stronger than the other. But you do not know at this point how to judge which weak things are stronger or weaker than the other. So it's always going to be a strong acid with a weak base, or a weak acid with a strong base. Always. Okay. Now, let's pick strong base, weak acid. Okay, so this is going to be a weak acid plus a strong base. Okay, really common weak acid, acetic acid. You'll recall acetic acid is HC2H3O2 or CH3COOH. But we're just going to write it this way. That's acetic acid, aqueous, and it is in fact weak. For a strong base, we'll pick the quintessential NaOH, aqueous. But I could just easily have KOH here, or BaOH2, or something. But just to be easy, we'll pick NaOH. Now again, it's really just a double replacement reaction. The H is going to go with the OH, the Na is going to go with the acetate, and I've got liquid water, and sodium acetate. Oh look, water and a salt. Yes, sodium acetate is still a salt. It's an ionic compound. Don't let the polyatomic ion fool you. This is my balanced chemical equation. Now, let's write the net ionic. Now, I started this by saying acetic acid is a weak acid. And if you'll remember back a couple pages ago, I said weak acids and bases do not dissociate completely in water. So that means when we're trying to write this net ionic equation, we are not going to dissociate the weak acid. We're going to keep it together. So this is going to stay HC2, H3, O2, aqueous. And the reason it's staying together is because in water, only a teensy little bit of this breaks up. 99.9% of it stays as this. So we are sticking with it. We are writing just this. Because remember, these net ionic equations represent reality. And the reality is, this guy doesn't break up in water. Not very much. So we're staying here. On the other hand, NaOH, strong. NaOH is going to break up in solution. Na plus OH minus. Now those are my reactants. The aqueous acid still together, and the base, the strong base, broken apart into its ions. Now products, water, of course, does not break up. There's water. Plus, now, sodium acetate is a salt. So it's going to break up. Salts, that's what salts do. They totally break up in solution. Na plus aqueous plus C2H3O2 aqueous. That's minus. Don't forget your charges. Now you'll notice the polyatomic ion does not break up. The only things that break apart in solution are ionic bonds, the bonds between positive things and negative things. Covalent things do not dissociate, and it is covalently bonded in there. So polyatomic ions do not split apart. Don't split them apart. But now, look what I've got. I've got acetic acid, I've got Na pluses, OH minuses, going to water, Na pluses, and acetic acid. What's my spectator here? I've only got one. Na plus. That's my only spectator ion. I cannot cross out this acetate and this acetate because here the acetate is still part of acetic acid. These guys do not cancel. Same as OH minus can't cancel with water because it's bonded over here. So now, to write the net ionic, I need H, C2, H3, O2, aqueous, plus OH minus yields water plus acetate ion. Aqueous there, liquid there. This is, in fact, the pattern for a weak acid plus a strong base. See how we have this as a weak acid plus a strong base? This is what the weak acid plus strong base is always going to look like. The weak acid still together plus OH minus, doesn't matter what that cation there was, OH minus yielding water plus the anion of the weak acid. That's always what it's going to look like. If you want me to write this generically, it's HA, where this is the weak acid, plus OH minus, that's the only part of the strong base we care about, the OH minus part, goes to water plus A minus. So it doesn't matter which weak acid we've got. It's always in the form of H pluses bonded to some anion, HA, plus OH minus goes to water plus A minus. That is a weak acid plus a strong base. Net ionic.